Hello everyone. Welcome to the Corona Characteristics Practical in the Laboratory Practice 5 module of Semester 7. Let's learn how to observe and analyze corona discharge in conductors. Let us consider two parallel conductors separated by a small distance. If we apply a potential difference between the two conductors, an electric field will be generated. The air around the conductor will ionize, and the electrons and the positive ions produced will move under the action of the electric field. If the potential difference is increased, at a certain level a complete electrical breakdown will occur. Now the air between the conductor do not act as an insulator. To avoid this, conductors in transmission lines are separated by a sufficient distance. However, the air around each conductor will still be ionized because of the high voltage levels which result in high field intensity. This ionization is corona discharge. The corona formation of a conductor can be categorized into 4 stages. When the voltage of the conductor is gradually increased, initially nothing will be observed. At a certain voltage a hissing noise is heard. This voltage is the disruptive critical voltage. If the voltage is further increased, a visible violet glow will be formed as patches along the conductor. This voltage is the visual critical voltage. As the voltage increases furthermore, the visible corona is formed throughout the conductor, and finally the medium will break down. Let's look how we can theoretically calculate these voltage values. First up is the disruptive critical voltage. It can be calculated by the equation shown. In this equation R denotes the radius of the conductor, D denotes the distance between the two conductors, and M0 denotes the irregularity factor. When the surface of the conductor is irregular, it is more liable for corona formation. Therefore, the irregularity factor is introduced. M0 is 1 for smooth polished conductors and reduces with the roughness. Simple delta denotes the air density correction factor. It is calculated by this equation. Next, to calculate the visual critical voltage, we use this empirical formula. Here, a new irregularity factor MV is defined. The rest of the symbols have the same meanings as discussed previously. Now we can calculate the theoretical voltage values. Corona formation causes several disadvantages. The main disadvantage is that it causes power loss in transmission lines. This power loss in turn causes a reduction of the efficiency of the power line and causes a voltage drop at the receiving end of the transmission line. It also leads to conductor corrosion because of the production of ozone gas during the process. Additionally, it causes electromagnetic interference. It is important to calculate the theoretical power loss expected due to corona discharge. The power loss can be calculated by this empirical formula. Here, F denotes the frequency in hertz, E denotes the phase voltage in kilovolts, and E0 RMS denotes the disruptive critical voltage in kilovolts. There are several ways that corona formation can be minimized and the power loss reduced. Corona formation reduces with the increase of the diameter of the conductor. Therefore, we can increase the conductor diameter. We can also use bundled conductors and increase the effective diameter. We can use corona rings to reduce the sharpness of the conductor curvature. These are some examples of corona rings and how they are used in transmission lines. Without further delay, let's start the practical. Make sure to note down the atmospheric conditions of the lab environment. First, you must connect the cylindrical-shaped wire mesh to the earth as demonstrated here. The connection of the high voltage source to the conductor is made through a liquid resistor. Here you can see the conductor connected straight along the axis of the cylindrical wire mesh. You have to take the readings of the string diameter and the mesh diameter. After arranging the wire mesh with the conductor, you have to close the door of the lab setup as shown here. This is done as a safety precaution. If the door is not closed properly, you can't turn on the breakers to operate high voltage sources, so that it ensures the safety of people. Next, you must go to the panel board of high voltage sources and turn on the relevant circuit breaker of the AC high voltage test control board with the main breaker. First, you have to power on the control board and should wait until the readings become stable. Then switch on the control board. After that, you have to increase the applied voltage gradually, using the step-up button, and observe the stages of the formation of corona, and you should record the respective voltages at which they occur. Make sure to wait for a moment after each increment. First, notice the disruptive voltage where you can hear the hissing noise. This value is equal to 21.1 kilovolts. Next, you can see the formation of visible corona throughout the conductor wire. This voltage is equal to 34.1 kilovolt. We need a high-resolution camera to capture the corona formation, even though it is visible to our eyes. So here we have shown a picture of a corona formation found on the internet. You can see this bluish color corona formation in a dark environment. Finally, you can observe the final breakdown of the medium at 48.1 kilovolts. After all these steps, we have to switch off AC sources from breakers and should discharge the capacitor as shown here. Use these observations when preparing your lab report. Thank you for joining this laboratory session.